Welcome back, everyone. Welcome to day 4 of Organometallics. Let me get myself the handouts. So we're going to start today's class by first spending about 10 minutes reviewing some of the topics that we went through very quickly at the end of last class. And there were a few questions towards the end of class and after class that people had that I thought would be worthwhile covering here to make sure everybody's on the same page. Then we're going to wrap up the worksheet from day 3 and cover the last topic that was supposed to be covered last class period, which is bonding. That will take another about 15 minutes. And then we'll jump into elementary reactions, focused primarily on ligand exchange and then on oxidative addition. The next class will cover all of the remaining elementary steps, and then from there we'll have a firm foundation for talking about catalysis. Okay, so to begin, let's quickly cover a few questions that arose while we were going through crystal field theory and ligand field theory at the end of last class. So there were some questions about the splitting energy, factors that affect splitting energy, and what this splitting energy actually translated to in terms of numbers that we think about on a daily basis. And so there are many factors that affect the splitting energy, which we denote delta. These include the nature of the metal, the oxidation state of the metal, the ligand identity. That's something we talked fairly extensively about last time, and then the geometry/coordination number. So one general trend is that higher oxidation state metals have larger splitting. And then, of course, another trend that we talked about last time was that stronger field ligands have larger splitting energy. So when you're trying to make it, when you're given a molecular formula of a complex you haven't seen before, of course, first you want to think about where the ligands lie on the spectrochemical series, whether they're strong field or weak field, what is the oxidation state of the metal, whether it's low oxidation state or high oxidation state, and then get a qualitative sense at least about what the splitting energy might be. A question came up about what the splitting energy actually translates to in terms of energy. And so on the worksheet that accompanied yesterday's class, or the Monday's class, these values were quoted in wave numbers. And so typically the splitting energy it corresponds to something that can be, where the electrons can be excited by visible light. And so that's 4,000 to 2,500 wave numbers, or in terms of wavelength, 2,500 to 400. And then I just did a quick conversion of these values into energy values. So it translates to 0.5 to about 3 electron volts, and 12 on the low end and 70 on the high end kcals per mole. So actually, this value is quite high. And I think that this will make sense when we talk about mechanisms like photodissociation of ligands, that you need to have this energy value be commensurate with the bond that you end up breaking. Okay, so hopefully that gets everybody situated in terms of how to think about splitting energy. And then another topic that I covered very briefly, and I think created a little bit of confusion because of how quickly it was covered, was this molecular orbital representation of group orbitals. And so this is a somewhat advanced topic. It requires, to take a deep dive into this, requires discussion of group theory, and that's going to be outside of the scope of this class. But I did want to touch on this again briefly, and you'll see that there's a handout that accompanies today's class on this, just so that everybody's at least conceptually on the same page with why this was brought up in the first place and how to think about this. And so when we're thinking about an octahedral metal complex and the 6 ligand orbitals that are going to be involved in bonding. Let's consider, like we did last class, a simple case where all of these are pure sigma donors. And then these 6 ligands collectively can be represented as these symmetry-adapted linear combinations, or sulks. And so these are linear combinations of basis functions like atomic orbitals that you're familiar with in MO theory, or vibrational displacement vectors. And so the point here is that we can think with analogy to atomic orbitals when we're building up a molecule from putting together atomic orbitals. We think about the various symmetry pairings. And that's the same case here. We're thinking about those same types of atomic orbitals now in 3 dimensions in an octahedral geometry. And so there are 3 sulks that we need to consider. And these labels, as I mentioned, come from group theory. And each has different symmetries. And in turn, the important thing is that each of these different symmetries then interacts with different orbitals on the metal that themselves have different symmetry. And this leads to bonding interactions in some cases, non-bonding interactions in other cases. And of course, anytime you have bonding, you also have anti-bonding. And so the reason that I think this is important to cover at least a little bit is that it sets a foundation for thinking about what orbitals are involved in bonding with the metals and which are non-bonding and thus enable back bonding, which will be an important theme of today's lecture. And if anyone does have additional questions about this topic, I'd be happy to recommend some additional reading on that or discuss it more outside of class. Okay, are there any questions as we wrap up what we covered last time and then jump into some new content? Okay, if not, let's talk quickly about bonding. And so probably you've already heard me refer to some of this nomenclature, but I think it's worth just defining so that everybody's on the same page. So in coordination complexes or organometallic complexes, there are 2 primary types of bonding. One is sigma bonding, where typically a lone pair or a pi bond of a ligand is going to associate to an unoccupied orbital on the metal. So based on the Salk analysis, this could be like the dz squared orbital or the dx squared minus y squared orbital. And this is sort of the most simple conventional kind of bonding. You see this in Werner complexes, for example. And then there's also, because of the filled d orbitals on the metal, so these are the dxy, dyz, and dxz orbitals, the metal can donate ligands, donate electron density back onto the ligands when there are energetically accessible and geometrically allowed orbitals to donate into. So here are 3 representative examples. One that's extremely important for the history and development of organometallic chemistry is CO back bonding. So carbon monoxide as a ligand is a relatively weak sigma donor to the transition metal, but it can nicely accept d electrons from a filled orbital on the metal. And I'll talk a little bit more in just a minute about the details of that phenomenon. Ethylene, we talked about this a few classes ago in the context of Zeiss's salt, this mysterious platinum complex that was isolated a couple centuries ago, 2 centuries ago now. And the question was, how do alkenes interact with transition metals? And that's in 2 ways. One, through the sigma bonding, and then also through this pi back bonding. And this is known as the Chat-Dewar-Duncanson model. And so in this case, we're donating into, in both cases here, we're donating into pi star orbitals on the alkene. So these are both referred to as pi back bonding. And then there's another kind of pi bonding where the ligand can first form a signal bond, and then typically a lone pair on the ligand is going to further engage in bonding by donating electron density to an unfilled d orbital of appropriate symmetry on the metal, and this would be called sigma donation. So this is commonly seen with halide salts, for example, with alkoxides as ligands. You have to have some lone pair here. So this, in this case, is a filled orbital of p, a filled p orbital on chloride that I'm depicting as engaging in pi donation. So back bonding to carbonyls is of special importance, both in terms of the history of organometallic chemistry and in terms of structure and reactivity. And so one of the consequences of pi back bonding is that because you're populating an antibonding orbital, the CO bond will become weaker. And so this can be read out directly in the IR. So the IR stretching frequency of free CO is shown here, 2,143 wave numbers. And metal CO complexes, in contrast, typically have stretching frequencies that are of much lower wave number, and so they can go down to as low as sort of the mid to high 1800s or 1900s. And so one of the ways that I like to think about this is that we know CO as a CO triple bond has a stretching frequency of around 2100. We know that CO double bonds, just from organic chemistry, like carbonyls, like ketones, esters, amides, etc., typically have stretching frequencies that are, say, 16 to 1800. And so as this metal CO bond begins to have more double bond character, so these are sort of two extreme representations. As this has more double bond character, of course, it goes to lower wave number. So more back bonding leads to lower wave number. And the dissociation, the energy of the metal CO bond itself is typically between 10 and 40 kcals per mole. And this bond, the metal CO bond, becomes stronger with increased back bonding. And the corollary there is the CO bond then becomes weaker in terms of with increased back bonding. Okay, so let's jump in to wrap up the problems of the day from last class. So we're going to go actually slightly out of order. So we're going to first cover 4 based on what we just talked about. And we're going to talk about 3 and use that as a springboard for MO diagrams of bonding and back bonding. And so just to read it out loud, question 4 says, for the series, and then it's a manganese carbonyl, chromium carbonyl, and vanadium carbonyl complexes, order the complexes by increased CO stretching frequency. So the question you should be asking here is, which of these are going to be more electron-rich and electron-poor? Are electron-rich or electron-poor metals going to be better or worse at engaging in CO back bonding? So take a minute to think about that. And as always, feel free to discuss with your neighbor. Okay, Cheng, what do you think?
So you just started.
Okay. Take a minute to think about it. So I think one of the first things, this would maybe be a hint to get you started, is to note where these metals fall on the periodic table. And to note that all of them have 6 CO ligands. And so this is what we'd refer to as an isoelectronic series of complexes. Any thoughts, Cheng?
I guess so. For all these 3 compounds, they all have 6 d electrons.
Okay.
And then they all have octahedral.
Great. That's a great start. So Cheng's noting that all of these are D6. All are octahedral. That is a great start.
And then now you need to consider the capability of each metal that contain their electron to the anti of the compound.
Yep, exactly. Okay, so that's you're almost there. So we've got it all set up. All of these are D6. It's an isoelectronic series. And then the question is just which of these metal centers is going to be more electron rich versus more electron poor. And so you can maybe just take a stab at it, and there's only two directions it can go, so you'll have a 50% chance. Okay, what do you think?
Vanadium best.
What do you mean best?
Donating electron to the anti-pi.
Okay, so if we order it in terms of increasing wave number, we'd expect, as you said, vanadium, by virtue of being most electron rich, is going to be the best at pi back bonding. That's going to weaken the CO, weaken the CO bond, lead to lower CO stretching frequency. Did anybody get anything different? And now, just to quantify this, here are the actual values. Perfect. Great job. Yeah, I think that you did. You approached this problem exactly the right way, which is to really just break it down into what you know, what you don't know, and then build it up from first principles. So great work. Okay, and now we're going to jump to problem of the day number 3. And we'll do the first part together. And then B and C you can do on your own. I'll ask for someone to help me with those. And the reason why we'll do the first one together is just so that you understand what I mean when I'm talking about MO, these energy diagrams from MO theory. So let's consider a generic L-type ligand bonding interaction. So remember that as you're doing MO theory and trying to qualitatively represent which electrons are at various energies. The ligand orbitals, because these are at a lower quantum number, are typically going to be lower energy than the metal orbitals. So an L-type ligand, I'll just draw, let's say, an amine as an example. And then, as we said, we're going to have some unfilled orbital on the metal. This could be dz squared, dx squared minus y squared. And then these are going to engage in some bonding interaction. So this is like a true qualitative MO diagram. Okay, and then the key is that because we're considering an L-type ligand, that in the system of electron content that we're using in this class, that we're drawing 2 electrons as coming from the metal. Okay, so let's consider these other 2 cases, one that you've heard about and one that you haven't. And so let's consider B and C. And I'll just give you I don't know if anyone has, maybe someone can jump in and define Z-type ligand for anyone who hasn't encountered that before.
Is it 2 electrons from the metal leading to an orbital?
Exactly. So it is the exact opposite of an L-type ligand, meaning that there's some filled d orbital on the metal that's donating to an unfilled orbital on the ligand. And it's a somewhat special, exotic case, so we're not covering that in any level of detail in class. But I would recommend we have a nice literature review by Joe on our website if anyone wants to read more about that. Okay, so let's consider 3B, Hansel. So generic X-type ligand, how will that be different than this case? So let's consider what's somebody's favorite X-type ligand? Flora. Okay. I made it even more confusing because I chose fluoride. But okay, no, let's just consider the sigma interactions at this point. Yeah, the question I guess I have is just about the electron. You're exactly right. The bonding is going to be similar, and then the question is just about which. Let's not do fluoride, it's confusing. Let's just do hydride. Very simple. So it's just about the accounting of which electrons are coming from what. So
the ligand will provide 2 electrons.
Yeah, I think you have it basically right. So in an X-type ligand, we're defining one. These bonds are more covalent nature. One electron coming from the ligand and one in the metal. Right, that's why the metal's oxidation state increases by 1 when it engages in bonding. Very good. And then last, Dongmin, the Z-type.
Yeah, so you're going to have 2 electrons, all coming from the metal.
Okay. Good. So now Dongmin saying that now we have empty orbital. Let's draw the boron, trialkyl, trisubstituted boron.
Z-type
Oh,
ligand?
sorry, this should be higher energy for this unfilled, I guess, right? Tyler?
Yes. And the sigma should be about the same.
About the same energy as the metal, right?
So if you have a Z-type ligand, does that increase your oxidation state by 2?
What do you think?
I would say, yeah, based on our previous analysis. Right, if you go up an oxidation state with an X-type ligand, then with it donating 2 electrons, it would go up 2.
Okay. Let's turn this over to our resident Z-type ligand expert.
So in general, for electron counting, it's easier to think of it as the reverse of an L-type in terms of the oxidation state. But when you start to go into Z-type ligands, really the idea that oxidation states of formalism really starts to come through. So in many cases, there's 2 thoughts in terms of how you count electrons, but you can just consider it a 2-electron donation to Lewis acid that doesn't change the oxidation state.
So, yeah, in case anybody didn't hear that clearly, when you start to think about Z-type ligands or more complex bonding, oxidation state, formalism tends to break down. So for the purposes of first pass analysis, you can just consider them reverse L-type ligands where there's not going to be a change in oxidation state. Thank you, Joe. And thanks for the question, Stephen. Okay, so now we're caught up. Those are the 2 problems of the day from last time. And so now we will talk about MO representation based on this. Using this as a springboard, talk about MO representation of back bonding interactions, and then we'll jump into problem of the day number 1. So if you want, you can look ahead to that. Okay, so here are these generic representations. I think, for me, this is always clear to just draw it like this first, but then it's also useful to think about how this looks like from an MO view as well. And so let's first consider the case of metal carbonyl complex. So as we said, CO has its electron pair that it's going to bring as a sigma donor. And then also at a much higher energy, you have the pi star that will end up being an electron acceptor. And then on the metal side, it's bringing with it filled d orbitals that could be any of the d orbitals I mentioned before, dxy, dyz, dxz orbitals. And then unfilled orbitals that thus, by virtue of being unfilled, are higher energy, like the dx squared minus y squared. And so, again, ligand orbitals tend to be, filled ligand orbitals tend to be lowest energy, then filled metal orbitals, then unfilled metal orbitals, and then unfilled ligand orbitals. So, again, this is not like a to scale, but in terms of qualitation, that's what you should be thinking about. And then the lone pair from the carbonyl is going to, because it's symmetry matched with this unfilled d orbital on the metal, it can engage in sigma bonding. And then the filled d orbital on the metal, because it's symmetry matched with the anti-bonding orbital of CO, can engage in back bonding, pi bonding. And then both of these have associated with them anti-bonding orbitals as well. That would be much higher energy, and I just don't have those drawn for the sake of simplicity.
Can you draw those dotted lines a little more clearly on the left side? I can't tell which one is connecting to which.
On the left side, sure.
So you have like this section where they cross over, and I'm not sure which ones go to which.
I'll draw these as solid lines with a break to try to make it more clear. And I will do the same down here because it's going to equally confusing. Okay, and then we could do this all day with many different ligands, but let's just consider one more representative and informative case. This is ethylene or any alkene. And so same general situation here. The only main difference is that the filled orbital from the ligand is going to be a pi orbital that's going to engage in sigma donation. So the nomenclature here is a little bit confusing. Pi orbital, but the bond at the metal is a sigma bond.
So the pi orbital zero, is that also going to mix with XZ?
The pi,
The bonding of the carbonyl.
I think it can in principle, but will be quite weak in nature compared to this bonding.
Okay.
So the next question is a good one, which is just, of course, CO also, you could think about donating this way, but I think because of for many reasons, including of the polarization of this molecule, that ends up being quite a weak bond. Does that make sense? So sigma bonding from the filled pi orbital of ethylene engaging again an unfilled orbital on the metal. I've simplified this further, so hopefully this is clear. Just metal with a lobe. This is a general representation of symmetry allowed orbitals here, and then the filled d orbitals, which are a slightly lower energy, forming the pi back bonding interaction by donating into the pi star antibonding orbital of ethylene. And so we mentioned that in the case of CO, this back bonding interaction is directly observable by IR, and one would thus predict that the back bonding to ethylene or an alkene should similarly be observable by various techniques. And that, I think, sets us up well for problem of the day number 1.
Also, that orbital, is that d z squared, or is it d x squared minus y squared without p? With sigma bonding.
Yeah, I've drawn this as a generic, so this could be either the dz squared or the dx squared minus y squared. And here you'll note I just drew as an example.
Okay, so both.
Both are symmetry allowed to engage in that. Okay, problem of the day number 1 from the day 4 worksheet asks you to consider 2 metal alkene complexes, both to zirconium in different ligand environments, and asks you to think about back bonding in both of these cases and to rationalize why one case over the other yields a significantly more stable complex. Okay, what do we think, Zhang?
I think the right one is more stable.
The right one is more stable. Walk us through your rationale.
Since we want to donate electrons into the anti-monoid orbital of the alkene, so the metal center is more electron rich, then it can interact better or donate more electron density into that pi bonding to stabilize the complex.
Okay.
And so the right one is like that's more
Okay.
electron rich.
So Zhang's offering a qualitative explanation that the one on the left looks cationic, the one on the right looks neutral. Is that sort of your thinking? And that the neutral one should be more electron-rich and thus more capable of engaging back bonding. Okay, I think that's reasonable. Anyone want to expand upon that or add to that?
Because the canonic complex is D0, so it cannot do back bonding at all.
Okay.
Whereas the right one is D2, so it can engage in back bonding.
Okay, very good. Thank you, Dong-min. So if you do a d-electron count of both of these complexes, you'll note that the one on the left, as Dong-min pointed out, is D0, and the one on the right is D2. And one of the important aspects of back bonding is that you need d-electrons on the metal. So,
How does this compare to the increased pi donation on the cationic design? Like how do those two, how do you balance those?
yeah, so it's a really good question. Metal alkene complexes, they have a spectrum of properties depending on whether the metal's early or late. So in late metal alkene complexes, they tend to be dominated by sigma donation, and thus more electrophilic metals are better. In the early metals, the early transition metals, they tend to be dominated by by back bonding, and thus more electron-rich metals form stronger interactions. And one of the things that if you take back bonding to an extreme, okay, so you can consider two actual representations. So this is zirconium 2. So you can consider when back bonding reaches an extreme point, then it actually can lead to what we'll cover later in today's class, oxidative addition, where you get a formal oxidation state increase at the metal, and now you're drawing these as actual proper sigma bonds. So if you wanted to say I proposed to you that actually a better representation of the compound on the right was this, how would you probe that? IR. Okay, that's a quick and easy one. IR, NMR, X-ray, looking at bond distances, all good ideas. And then the other point here is that this will build off of Tanner's question. So late transition metal alkene complexes, they tend to be electrophilic. So we'll come back to this point, so you don't have to worry about this now. But if you consider these two cases, complexes like this are electrophilic at the alkene carbon atom, and complexes like this are nucleophilic at the alkene carbon atom because there's so much back bonding. Okay, very good. So let's keep charging forward. Now we'll talk about elementary reactions that can change the coordination environment around the metal. And we'll start this out by discussing what's called the trans effect or trans influence. And so the first thing I'll point out is just a nomenclature issue. The trans effect is a kinetic phenomenon. Trans influence is a thermodynamic phenomenon. And people don't always use this nomenclature correctly in the literature, so it can create some confusion. But trans effect, we're typically talking about rates of ligand substitution. Trans influence, we're talking about things, data that can be measured of well-defined intermediates that are at their ground state, like bond length or stretching frequency. Okay. And this is most important. Trans effect is most important for D8 square planar. That will become hopefully clear in a minute why that's the case. And essentially the definition of this effect is that ligands, I'll just write this out, ligands that are said to be high trans effect ligands are more effective at labelizing a ligand trans to themselves. And this, I think, is clear if we just draw this. And so if we're talking about trans effect, we're considering this ligand and the rate of substitution trans from it. And empirically, there are some well-defined trends. And one of the things that can be confusing is that these trends depend a little bit on what metal you're doing this measurement with. And so you'll look in one textbook and you'll see one trend, and a different textbook, a slightly different trend, but overall will be the same. So I'll write out the one that's in the Hartwig textbook. And if you find a different one and you like that one, that's fine. I think this question came up last time I taught this class, and we went into the literature and actually figured out what how they were making this determination in different cases. So there are some general trends that are worth commenting on. So things that are ligands that are very strong sigma donors and or pi acceptors. And so phosphine, I've shown here, is typically a strong sigma donor and a pi acceptor because of it has an unoccupied orbital on phosphorus. We'll come back to that when we talk about ligand design principles, but phosphine is a strong sigma donor and a pi acceptor. It's a strong trans effect ligand, like others in this class, CO, CN, olefins, and then these are just extremely strong sigma donors. And then some of the weaker trans effect ligands are those that are somewhat weaker sigma donors and or pi donors as well. And so like on a say on an exam, we probably wouldn't ask you, to distinguish between things that are very close, like ammonia versus a primary or secondary amine. But if you're asked to distinguish between cyanide and OH, we'd expect you to be able to do that. Okay, so this now with this rule defined, let's consider problem of the day number 2 from day 4. Basically, it just asks you to apply the trans effect to considering these 2 platinum complexes. So take a look at that, and I'll jot some more notes on the board. Okay, problem of the day number 2. First one, Elena, what's going to happen in the first step? Okay, you will coordinate ammonia, and ammonia will displace a chloride, okay? And in this case, they're all the same, doesn't matter, so I'll just draw it here. Okay, then what?
Well, on the list, they're pretty similar.
Mm-hmm.
And so I don't know if they're much selectivity for every.
Okay, let's say that it's selective. Then what's going to happen?
That it would be transitive.
To the amine. Is that what you said? Okay. So Elena is saying that if you just look at our list, ammonia is a stronger trans effect ligand than chloride, so we'll get substitution. Trans in this case.
So does the list mean the opposite of what it says?
Oh, sorry. So what did you say, Elena? You said that it's cis to the... Okay, so which of these is a stronger trans effect ligand based on the list? Chloride, yeah. Okay. So we're considering which of these is a stronger trans effect ligand. And if we just go to the list, we see that it's chloride. And so then we're going to substitute trans to chloride. This is like the classical example of trans effect. If anyone's already taken organometallics, you've probably seen the exact same thing. Okay, and someone want to shout out the name of this? Cisplatin. Common anti-cancer drug. Okay, and then just very quickly, just the opposite order. It's just not here. The max.
So it's going to be the opposite case. So you'll just replace ammonia with chloride first, and then you'll get, I guess, transplatin at the end.
Okay. So, and then in this case, you have the same question. You're asking displacing trans to ammonia or trans to chloride, and chloride wins out again. But in this case, because the starting material is different and the ligands that you're exchanging in are different, you would get transplant. Very good. Any questions on that? And so the origin of the trans effect has to do with the mechanism of ligand exchange, what we're going to talk about next, and the fact that typically D8 square planar complexes, let's see, they have 16 or fewer electrons, and thus are able to engage in what we call associative ligand exchange, where they can first form an interaction with an incoming ligand, and that gives you, I didn't draw this very well, so this might be confusing, but this gives you a trigonal bipyramidal intermediate, and then some ligands here are better at stabilizing this intermediate, because so the trans ligand ends up being in axial position, and so depending on its ability to be sigma donating and pi accepting, it's more or less stable here, and thus the slow step will be accelerated, and then the collapse of this with loss of the outgoing ligand gives the exchange. And so there's another competing effect, which is called the perhaps not so creatively, the cis effect, and that turns out to be more important for octahedral complexes, so we'll talk briefly about that later, but that is also at play. So of course, like all things in life, it's more complicated than this rule, and so the ligands cis here also play some role, but for first approximation for square planar complexes, you can always follow this rule. It's going to get you right most of the time, but you do have to consider these in some more complicated cases. Okay, good. Any questions on that? Does anybody need this part? Okay, so let's talk about a little more terminology. So now we're going to be talking about reactions that modify the coordination environment around the metal and also that modify the organic fragments that are involved in these coordination interactions. And so just to make sure everybody's on the same page, we'll be using this language of spectator or ancillary ligand, actor, reactive ligand. So basically, in the reactions we're going to be learning about, some ligands are involved directly and some are involved only indirectly. And so let's just consider this substitution reaction, or this, initially this substitution reaction. So the first step is going to be loss of this phosphine ligand. To give a vacant coordination site. Often we're going to use these boxes to represent open coordination sites. Next step is we're going to coordinate and define. This chemistry is not so important other than I'm just trying to make a point about the nomenclature. And then this is actually going to go on to do a cyclotrimerization to the okay, but this is not so important. And then the nomenclature is that this ligand, because it's involved in dissociation, will be an actor. This one, these are degenerate, so I guess this one is also an actor. And then these two are going to be ancillary or spectator. And you'll notice as you see more examples, some ligands are almost always spectator ligands because they're really tightly bound to the metal, like CP is the case of that. Chloride in this case could also fall up in this bin. Okay, so let's talk about, we alluded to the mechanistic considerations of ligand substitution here, but let's talk about that now in more detail. So there are two general pathways. Associative, typically, as we saw with 16 electron complexes, the overall general scheme will look like this. Bring in a new ligand, Al prime. We're going to form some intermediate that's most likely going to be an 18 electron intermediate, coordinatively saturated, and then the last step will be loss of one of the original ligands. And the other major category is dissociative. Typically, going to see this in 18 electron octahedral complexes. There are some exceptions we'll discuss. And essentially, this is just the opposite order of events. I'll draw it out just so everyone's on the same page. And so I think one of the powerful things that comes out of this is that just by doing the same kind of analysis that we've done already now many times, where you do electron count and figure out the geometry. You can begin to get a sense of what elementary reactions are most likely to happen. And there's an important exception to this general phenomenon where dissociative pathways are common with 18 electron complexes. So I'll draw that out here. And that's ligand slippage, which people also call haplotrophic shift. So earlier we learned about the term hapticity, and this just basically means that things are switching their hapticity. Okay, so let's consider this ruthenium 1 complex. I guess this is probably ruthenium 2, but counter ion. Okay, let's just draw this. I might have this wrong in my notes. Okay, so let's assume this is an 18 electron complex. Normally, if you're talking about ligand exchange, in this case, you'd go to this rule and say, well, it has to be dissociative. We have to lose CO, but loss of CO can be slow in some cases. And so if we want to bring in a phosphine ligand, how is this going to work? And what can happen is actually the CP can slip off. Very clever trick, where it goes from being eta 5 to eta 3. So remember, CP is a 6-electron donor. An allyl fragment, so this is now essentially just an allyl fragment, is a 4-electron donor, so now we go down to 16-electron. And we can proceed via an associative pathway instead. And this process of ring slippage can be accelerated in one important subtype of systems. Some of you maybe will be familiar with this. So when this is an indenal fragment, then upon ring slippage, you get to a very stable high-al intermediate, and this is a special class referred to as the indenal effect. So it's found empirically that if you switch CP to indenal, and you often get dramatic rate acceleration in terms of ligand exchange, and that's due to the indenal effect, where putting a fused arene here facilitates ring slippage, and this was first proposed by Fred Basolo. One of the defining features of these two pathways is that they have different kinetic behavior. And so if we consider the dissociative pathway, we're considering carbonyl or CO dissociation. When we draw things with an open coordination site, often in practice there's some solvent molecule or something temporarily occupying that position. So in a dissociative case, most commonly, though not always, but most commonly, the slow step is going to be the dissociation step, and thus the overall rate is going to be, the rate equation will be overall first order and specifically first order on the starting complex. So this step this is slow, this is fast. And anytime you have one step that's in equilibrium followed by an irreversible step, it does depend on what the relative activation energies are, but in most cases it's the situation I've drawn here. And then in the associative case, you add the new ligand. The step will be slow, the step will be fast, and the slow step is now a bimolecular process. And so the key difference is now that you have rate dependency on the incoming ligand. And so in a new system where you haven't encountered before, making these kinds of rate measurements can be a way to disambiguate. There's another distinguishing feature that I'll just talk about, and I don't have notes jotted up on this, but another way that you can just make this distinction is if you do an Eyring analysis that allows you to determine the enthalpy and entropy of activation of the reaction, and thus the rate determining step. And systems that proceed via a dissociative pathway, where this is the slow step, that involves breaking this bond, lengthening this bond, and so these tend to have a positive entropy of activation because the transition state is more disordered than the ground state, and these that I'm getting to a point where I just have to do some writing on the board anyway. The associative one will tend to have a negative entropy of activation. And so these two processes, especially if you look at the rates, the rate equations, you'll notice that these are directly analogous to SN2 and SN1 in organic substitution. because sometimes the activation energy for ligand exchange can be quite substantial, often loss of CO is one such case. You need ways to facilitate ligand exchange. I'll just jot those up here. So here are some representative examples. If you want to exchange out a halide salt, a common trick is to add a silver 1 halide scavenger. The driving force here is, of course, loss of silver chloride or the silver halide. If you have a metal hydride, you can often directly protonate it to give H2 gas. And with CO, you can, and other ligands as well, you can photodissociate, so radiate with light, and that can blow off a ligand. And then these are both examples of transmetallation processes that are should look vaguely familiar to what we covered in the main group lecture.
Methods 5BMX, MH, LH.
Sorry. Thanks, Stephen. So I'll briefly cover now the cis effect. This is more important for octahedral complexes. So trans effect, if you have square planar complex, you should be thinking trans effect is going to dominate. If you have octahedral complex, there'll be some trans effect component, but the cis effect will also be very important to consider and arguably dominant. And so let's just draw this up. And so in this ligand exchange, there are two scenarios. So this is the trans ligand of interest, and this is these are all cis ligands. So this is trans, this is cis. There are more of them. And so after dissociation of one ligand, you'll note that we get to a 5-coordinate intermediate that is vaguely familiar to what we get with via association to a square planar. And now you have a question of which of these is going to be more stable, and formation of this, which is what's going to, so you have a vacant coordination site here, essentially. You can think of it that way, but there's some geometric reorganization. This is going to be favored by bidentate X, or at least ligands that can be bidentate and destabilized by strong sigma donors and strong pi acceptors. And so then the general trend, it's almost opposite of the trans effect, but not quite. If you don't want to jot this down, this is in the textbook, so there's nothing you can't find elsewhere. So this is a metal acyl species, probably not drawn that clearly. So it looks, as I said, vaguely like the reverse of the trans effect. But one of the things you'll note is that the best cis effect ligands are those that are capable of coordinating in a bistentate fashion. So an example of that, I'll just draw it here, would be acetate, which can then go kappa 2 after loss of the outgoing ligand, and likewise for nitrate, formate, etc. There have been proposed, and there is evidence for more complex ligand exchange mechanisms like interchange or ligand exchange mechanisms that are associated with electron loss or electron gain. I won't cover those, but there is some nice examples of that in the textbook. So at the remaining time, let's tackle problem of the day number 3, and then I'll just get us started with a few notes on octave addition to set the stage for next class. Okay, problem of the day number 3 asks us to consider this diethylene rhodium CP complex, as well as its ligand exchange product. Follow our standard workflow: coordination number, oxidation state, total electron count, and then design an experiment to disambiguate between the two possibilities, associative or dissociative. Okay, problem of the day number 3, part A. Vincent.
The coordination number is 5 for each of the complexes.
Okay.
The oxidation state is 1 for both of the complexes. And the total electron count is 18 for the complexes.
Okay. Did anybody get anything
Oh, sorry.
different from that?
No, I'm going with 18.
You're going with 18
Yes.
for both. Okay. Is that your final answer? Everything on the line. Anybody get anything different from that? Okay, very good, Vincent. So we're in a situation that looks like typically we'd expect to look like a dissociative pathway. 18 electron complex is a starting material. Kai, what about B? How would you design an experiment to determine the mechanism of ligand exchange?
First, I think you can measure the kinetics and to see if it is bi-molecule or single molecule kinetics.
Okay, specifically, can you just describe, just so everyone's on the same page, what's the kinetics experiment you would do? You measure the rate of the exchange reaction under what different conditions?
Maybe from the bad starting material, you can just add the phosphine ligand into it and to measure the rate of the ligand exchange for the phosphor use NMR.
Okay.
And you can get the equation for the rate. Yeah. And,
Okay, so let me just repeat that so everybody can hear. So the idea Kai's proposing is we'll do an experiment. We're going to do an NMR experiment. We're going to look at phosphine NMR. Triphenylphosphine free versus bound is going to have different chemical shift. And then he's going to set up this experiment with different initial concentrations of triphenylphosphine, let's say 4 different concentrations, 4 different NMR tubes. And then you're going to measure the initial rate. And you're going to ask the question, with more phosphine, does the exchange go faster or does it stay the same? Okay?
And furthermore, you can maybe use the Indino effect to change the CP into Indino to look if it can facilitate the ligand exchange.
Okay. And so the other idea is that we can use other ligands and other complexes in this family, so change CP to indenyl or to other substituted CPs, and then ask, is the exchange going faster or slower? Again, using NMR or another technique. And if there's a big indenyl effect, then that would be consistent with associative pathway. Anyone else have ideas for B?
You like reactor?
Yeah, you could do. I think the technique is not. There are many techniques you could use. I think for something like this, phosphorus NMR is a good choice because you're only expecting to see 2 things, and whatever else happens, you'll be able to track that rate. React IR, one of always the challenges is you've got to find signals that correspond to your starting material and your product, and they have to be in areas that are clean. Okay. Yeah, and then I would say one other thing you could do. I mean, the rate experiment is the most obvious one. The other thing is that you could do a experiment. You could create an I-ring plot, and then from that back out the entropy of activation, and we'd expect that to be diagnostic of whether it's associative or dissociative. Dissociative would have a positive entropy, associative would have negative entropy. Okay, good. We're just at the end of the time here, but let me just prime you for what we're going to be talking about in the next class and maybe into the class following, which are elementary steps. So now we've talked about reactions that can change the coordination environment of the metal. We want to dig into reactions that can change the composition of the ligands involved. So reactions that start to modify the organic fragments that are involved in association, dissociation, et cetera. And so the first step that we're going to talk about in detail next class is oxidative addition. You've already seen this in the context of formation of Grignard reagents. If you take alkyl bromide and you add magnesium turnings, that's an oxidative addition process because you go from magnesium 0 to magnesium 2. More generally, it's just any reagent that will engage in that will coordinate to the metal and then increase the metal's oxidation state by 2 while simultaneously forming 2 new bonds to the metal. And this can actually be, these 2 units can be tethered together as well, or they can be distinct. Just like in, so oxidative addition can be viewed as like an extreme of back bonding. It's back bonding taken to the extreme. The back bonding is so intense that it actually severs the donation to the antibonding orbital is so intense that it actually severs the bond of interest. And so just like with back bonding, you need to have d electrons on the metal. You cannot undergo oxidative addition with T0. This is a common homework or exam question where they'll ask, people ask you to consider oxidative addition of some D0 complex, and because it's, later in the semester, you're not thinking to just take it back to the basics and realize it's D0. And then one of the key trends that we'll come back to again and again and again is that because during oxidative addition, you can actually, if you like arrow pushing, you can draw this as pushing arrows like this. This bond maybe be more accurate. And so because the oxidative addition involves electron transfer off the metal, it stands to reason that electron-rich metal centers will be more reactive in oxidative addition, and that's indeed the case. And thus, in terms of ancillary ligand design, ligands that make the metal more electron-rich, such as strong sigma donors, tend to facilitate oxidative addition. And the opposite is also true. High acceptors like CO, they tend to diminish the rate of oxidative addition. So, we saw this tungsten carbonyl complex down here. That would not be a good candidate for oxidative addition. And then anything that can facilitate negative charge buildup on the metal is also good for oxidative addition. So we'll leave it at that. We'll start off the next class by talking about different classes of AB reagents that can engage in oxidative addition, and then the mechanisms by which that can take place. And then we'll just keep plowing right along through to reductive elimination, transmetallation, migratory insertion, building up the toolkit of elementary steps, and then putting them all together in synthetically useful catalytic processes. Okay, thank you very much. We're dismissed.